Hello, everyone. In this section of Electronics 1, we will introduce diode applications related to limiting and clamping circuits. In the earlier section on the basic structure and equivalent circuit of amplifiers, we mentioned that an amplifier output has upper and lower voltage limits. In practice, we usually do not want a circuit to operate too close to these extreme voltages because that may make the circuit easier to damage. Therefore, we need a limiting circuit to restrict the maximum or minimum value of the signal voltage and prevent the signal from reaching the critical voltage level during transmission. This voltage limiting function can be achieved by using diode devices. First, let us look at the first limiter circuit. As shown in the figure, only a resistor in series with a diode is needed to build a basic limiter. When the input signal Vi is greater than 0.7 volts is forward biased and turns on. Based on the constant voltage drop model, a conducting diode can be modeled as an element with an approximately 0.7 volt voltage drop. Therefore, the output signal VO is limited to about 0.7 volts. When Vi is less than 0.7 volts, the diode is off and behaves like an open circuit, so VO equals Vi. From the transfer characteristic on the right, we can see that the positive voltage of the signal is clipped at about 0.7 volts. Next, we introduce the second circuit, which is obtained by reversing the diode direction in the first circuit. In this case, when the input signal Vi is less than negative 0.7 volts, meaning it is more negative than negative 0.7 volts, the diode becomes forward biased and turns on. Therefore, the output signal is limited to about negative 0.7 volts. When Vi is greater than negative 0.7 volts, meaning it is more positive than negative 0.7 volts, the diode is reverse biased and behaves like an open circuit, so VO equals Vi. From the transfer characteristic on the right, we can see that the negative voltage of the signal is clipped at about negative 0.7 volts. Now let us look at the third circuit. Two diodes, D1 and D2, are connected in parallel but in opposite directions, as shown in the lower circuit. When the input signal Vi is greater than 0.7 volts, D1 turns on, while D2 is reverse biased and remains off. Therefore, VO is approximately equal to the forward turn-on voltage of D1, which is 0.7 volts. When Vi is less than negative 0.7 volts, meaning it is more negative than negative 0.7 volts, D2 turns on, while D1 is reverse biased and remains off. Therefore, VO is approximately negative 0.7 volts. When Vi is between negative 0.7 volts and positive 0.7 volts, neither D1 nor D2 is forward biased, so both diodes are open circuits and VO equals Vi. From the transfer characteristic, both the positive and negative signal voltages are limited to within plus or minus 0.7 volts. Next, we introduce the fourth circuit. This circuit is based on the first limiter, but now the diode is connected in series with a fixed voltage source. Here, we use 10 volts as an example. For the diode loop to conduct, Vi must be greater than the diode forward voltage, 0.7 volts, plus the fixed 10-volt source. In other words, only when Vi is greater than 10.7 volts will the diode loop turn on, and the output signal will be limited to about 10.7 volts. When Vi is less than 10.7 volts, the diode cannot conduct, so the loop is open, and VO equals Vi. Compared with the first circuit, adding a fixed voltage source in series with the diode allows us to adjust the positive limiting level. Using the same idea, if we reverse both the diode and the fixed voltage source in the fourth circuit, the diode loop will conduct only when Vi is less than negative 10.7 volts, meaning it is more negative than negative 10.7 volts. Once the loop conducts, the output signal is limited to about negative 10.7 volts. When Vi is greater than negative 10.7 volts, the diode cannot conduct, so the loop is open and VO equals Vi. Compared with the fourth circuit, changing the diode direction and the polarity of the fixed voltage source allows us to adjust the negative limiting level. What happens if we replace the diode in the first circuit with a Zener diode, as shown in the figure? The characteristic of a Zener diode was introduced in an earlier section. Under forward bias, it behaves like a regular diode. Under reverse bias, however, when the reverse voltage exceeds the Zener breakdown voltage Vz, a large current can flow and the diode conducts. Therefore, a Zener diode can also turn on under reverse bias once the reverse voltage reaches VZ. For the sixth circuit, the transfer characteristic between VO and VI can be described as follows. When VI is greater than 0.7 volts, the Zener diode is forward biased and turns on, so VO is approximately 0.7 volts, just like a regular diode. For reverse bias, if VI is less than negative VZ, meaning it is more negative than negative VZ, the Zener diode conducts in reverse breakdown, so VO is approximately negative VZ. When VI is between negative VZ and 0.7 volts, the Zener diode is off and behaves like an open circuit, so VO equals VI. Similarly, if we reverse the Zener diode in the sixth circuit, we obtain the seventh circuit shown in the figure. When VI is greater than VZ, the diode conducts in reverse breakdown, so VO is approximately VZ. When VI is less than negative 0.7 volts, the diode is forward biased and turns on, so VO is approximately negative 0.7 volts. When VI is between negative 0.7 volts and VZ, the Zener diode is off and behaves like an open circuit, so V equals VI. Now, what if we connect two Zener diodes back to back, as shown in the eighth circuit? After looking at the previous 7 circuits, we can see the main idea very clearly. When the diode loop is open, VO equals VI. When the diode loop conducts, the output voltage is clipped. Therefore, the key point in analyzing a limiter is to determine under what condition the diode loop begins to conduct. Once that condition is known, the limiting voltage can be found. Since the two Zener diodes are connected in opposite directions, when one diode is forward biased, the other diode is reverse biased. First, consider the case where VI is positive. D1 is forward biased while D2 is reverse biased. For the diode loop to conduct, D1 needs about 0.7 volts to turn on in the forward direction, and D2 needs about VZ to conduct in reverse breakdown. Therefore, both diodes conduct only when VI is greater than VZ plus 0.7 volts. In this case, the output voltage is clipped at approximately VZ plus 0.7 volts. Using the same idea, when VI is negative, D1 is reverse biased and D2 is forward biased. For the diode loop to conduct, D1 must enter reverse breakdown, which requires about negative VZ, and D2 must be forward biased, which requires about negative 0.7 volts. Therefore, both diodes conduct only when VI is less than negative, the quantity VZ plus 0.7 volts. In this case, the output voltage is clipped at approximately negative the quantity VZ plus 0.7 volts. When VI is between negative the quantity VZ plus 0.7 volts and positive the quantity VZ plus 0.7 volts, the diode loop cannot conduct. Therefore, the loop is open and VO equals VI. Finally, we can see that this circuit limits both the positive and negative voltage levels. This is called a double limiter. This concludes the introduction to limiting and clamping circuits. Please look forward to the next lecture. See you next time. Bye-bye.